Welcome to a series of presentations about piano. I will start by reading out a few basics. Piano is a tool that accurately models the behavior of commercial planes from scratch. It gives the performance, carbon emissions and design size and characteristics of real or projected airliners, business jets, turboprops and other conventional subsonic types. It has been around for 3 decades and has become something of a de facto global standard, largely due to its database of more than 600 carefully calibrated aircraft models. It's used by many airframe and engine manufacturers, research, governmental and intergovernmental institutions worldwide, and several of these are listed in piano.aero. You can take a look at that website. I do not update it regularly, but there is a lot of interesting stuff there, including the full user's guide, examples, and a bit of history. You're looking at the screen of my iMac, and within that iMac there is also Windows 10 running. And in a moment we will start Piano from here. Piano uses a data folder that contains all the information that it needs. Primarily that means the planes database. There is also an engines database and other stuff here. Let's take a look at the planes first. There are more than 600 of those in the database. You can define new ones from scratch, or you can modify and adjust any of the existing ones in the database. The size of the files is tiny. Typically each contains 80 to 100 parameters. There are more than that available, but that is a typical number. Let us take a scroll down. I can show you inside one of these files. There are simple text files, so they can be opened up with any text editor. You don't need to look inside these, but if you want to, you can. Let's take a look at the engines. Engines are data sets that describe engine behavior under all flight conditions. They're normalized, which simply means they can be scaled to any thrust. That's what's called rubber engines in the industry. They have generic names, but they derive from real engine data. One engine can be used by many different airplanes, adjusted individually by factoring the various ratings and fuel flows up and down to represent different related engine types. And you can also add new engines if you have access to the relevant characteristics. At this point you should have a lot of questions, like how these planes are generated, the kinds of methodologies that are used. This will be a long series of lectures, and I will answer such questions gradually as we go through. You will also wonder how the models are verified, how they're calibrated to reflect real behavior of actual aeroplanes accurately. And I will read another slide for you. Aircraft models in Piano's database are created totally independently by LYSIS using a great variety of public and private sources. No endorsement of any aircraft model by any manufacturer or by any other organization is ever sought or implied. LYSIS has no cooperation agreements with or any vested interest in any manufacturer or other organization. There are no industrial biases or hidden agendas behind any aspect of the database or in any sample aircraft analysis you see here. Just 3 decades of objective, professional, intense SWOT research. Now, as we go through the coming lectures and start generating aircraft models from scratch, you will understand quite a lot about the process of calibration, and this is very important and is one of the main aims of these lectures. For example, I will later accurately model a 787 and an A350 starting from a common origin. But for the moment, enough said. For the rest of this session I will focus on running the database. Let's start Piano. It has a very simple interface. I can make it simpler still by clearing out all the blurb. So basically you get a blank sheet of paper and a good old-fashioned menu bar. We will run everything through here. For example, we can look at 3 views, geometric reports, mass statements, drag characteristics at a spot point condition, tabulations, design range calculations, takeoff and landing field lengths, can look at payload range diagrams, off-design missions at a specified mass, or off-design missions at a required target block range, block distance. Many other things. There is a flight menu through which you can generate flight maneuvers, and you can string these together to generate sequences, and that can represent any subset of an entire flight or an entire flight itself. You can then edit the segments, you can iterate them to achieve specific endpoint conditions, you can save them on file and run them again later. So this is a very powerful feature. There is a CO2 menu, and you can calculate transport capability and transport efficiency of individual aeroplanes here, or you can look at these characteristics for the entire database in an overall sense. And you can also calculate ICAO CO2 metric characteristics if for whatever reason you have an interest in those. There is a little bit more to the interface, and I will show you it here. So later on, when we're doing design exercises, we will be looking at palettes of parameters. So this is a palette, this is the palette chooser. So you can enter and examine parameter values here. You can also select your combination of unit choices, but we will not be doing things like that in this session. So I will just close it off. For this session we will only need the menus, and in fact I will be using keyboard shortcuts quite extensively. So things will be happening rather spontaneously, but all of these shortcuts are shown in the menu. So if you actually have a copy of Piano in front of you, you will be able to figure out everything pretty much instantly. So this is pretty trivial stuff. So let us go and load an aircraft. I will load this model of a Boeing 787-8. Piano has loaded the file and it's checked it. It's also loaded the engine model that is associated with it, and it's done a sequence of geometry, mass and balance calculations, at the end of which you have an aeroplane with a fixed set of weights and a fixed geometry, including a fixed tail in this case, because this is a database aeroplane, it is not a design exercise. We can look at the geometric report. You get various definitions of wing area, Airbus definition, Boeing's Wimpress definition, other characteristics, fuel capacity, geometric fuel capacity, fuselage characteristics, wetted areas for individual components and for the whole of the aeroplane. You can also take a look at the 3 view of the aeroplane, and you can look at it that way or that way as well. It's worth pointing out that everything you see on the screen is calculated on demand based on the 80 to 100 defining parameters that are kept on file. And that goes for whenever you ask Piano for any kind of information. We can look at the mass breakdowns, mass characteristics. These are in kilograms. Since this is a US aeroplane, I can go and change to pounds and do my report again. So MTOW 502,500 pounds, maximum landing weight 380,000, maximum zero fuel weight 355,000, that's the certification weights. We have an operating empty weight of just under 260,000 pounds, and that goes with a configuration for 242 passengers. That's your payload, and the remainder is the fuel and in this design condition. Within the box you can see the breakdowns that get put together to build up the OEW. So you have structure, engines, fixed equipment, etc. And over here they are in more details: wing group, fuselage group, etc. The mass breakdowns are preliminary design estimates. For a design exercise that is significant, but for a fixed aircraft it makes no difference whatsoever to performance. The certification weights and the OEW are set to suitable values, and that is all that you need for performance calculations. and that goes for the entire database. From the geometry we can do drag calculations. Let's look at a flight condition of Mach 0.85, 37,000 feet, and you can enter a lift coefficient or a cruise mass. So let's say 200 tons, 200,000 kilograms. Here is your drag report. So this flight condition corresponds to 487 knots true airspeed, 278 calibrated. There are drag coefficients, zero lift, lift induced, compressibility, trim, and a variety of corrections. Zero lift component breakdowns of wing, fuselage, and others. The number that matters, the overall lift to drag ratio at these conditions, about 20.7. Fuel flow and performance reserves, or residual rate of climb at these flight conditions. We can also look at the overall lift drag polar. Let's say at 39,000 feet, the altitude is only needed to get the right Reynolds number, and that is done in all calculations in Piano. So this is your polar, lift coefficient, lift to drag ratio. Each color is a different Mach number. So the pale blue is Mach 0.85, which is typical of this kind of airplane, and we get peak lift to drag ratios in the region of 20.5, 20.5. To those of you that are aerodynamicists, if you are intrigued by the slight kinks over here, this is just an artifact of a simple aeroelasticity correction that is included in this case. We'll be talking about such details later on. The drag breakdowns are preliminary design estimates. Again, what matters to performance is the overall polar, which will include adjustments in each case. We have loaded an engine, and so we can derive engine performance at any spot point condition. At the moment, the engine is sized to 70,000 pounds of reference thrust. There's a bit more available at takeoff. That is just an increased takeoff rating that is available, but the reference thrust is 70,000 pounds. And let's say at 35,000 feet and Mach 0.85, this engine produces a maximum cruise rating of 14,700 pounds, an associated fuel flow, SFC in the region of 0.54. Similarly, the max climb rating and max continuous rating, max takeoff not available at this altitude, and idle characteristics. I can also enter any intermediate thrust that I may need. So for example, if I need 12,000 pounds of thrust under these conditions, then my corresponding fuel flow will be 2,917 kilograms per hour. Let me just digress for a moment. I'd like to show you how seamless the environment is and how you can instantly transition between doing database analysis and design changes. So I can go and straight away load a different engine. This is the current one. Let me load an entirely different model, which has now automatically been sized to the 70,000 pounds reference thrust. And if I look at its characteristics, I can see now that the max cruise thrust, for example, it has gone up to 15,900 pounds, and the SFCs are near the region of 0.59. I can also change the aeroplane itself. So if I look at the aspect ratio, it's 10.5 at the moment. That's by trapezoidal definition, and that looks like this. If I pop up the dialog again and reduce my aspect ratio to, let's say, 8, do the drawing again, you will see that as soon as I asked for the drawing again, it did a geometry mass balance calculation, so everything has changed. The wing is, as you can see, stubbier now, and if I look at the aerodynamics, the peak lift to drag ratio is now down quite a lot, nearer to 18.5. So this is a completely different and redesigned aeroplane. But I can now go and revert to my original aeroplane straight away, and I am back to my 787 as I was before. Let's now start looking at performance, and that will be calculated individually in each case from first principles. Let's ask for some specific air range information. So you have specific air range in nautical miles per kilogram here as a function of Mach number, and each color is a different weight. This curve is the locus of maximum specific air range, and this is the locus of 99% of maximum SAR, which would be the LRC condition, long range cruise. So that's long range cruise, that is maximum range cruise. You can do these curves at any altitude. We can look at the plot of mass versus altitude. So as the aircraft weight reduces throughout the flight, the altitude increases. So the blue line represents the optimum altitude. The green jagged line is the profile that the aircraft actually follows given the flight levels that it is allowed to operate at, and it will track the blue optimum line as closely as possible. The red and brown lines are limitations in thrust capability. There are many other things that we can look at, but let's look at design range calculations straight away, the most interesting bit. And this is our design range, which is flown at MTOW. And with 242 passengers, the nominal payload about 23 tons over here. So the total distance is 7,725 nautical miles. The block fuel burn about 79 tons. And a set of emission characteristic calculations, NOx, hydrocarbon, CO, and of course the CO2 generated. And all these calculations are subject to maneuver allowances and a set of reserves, in this case 200 nautical miles, 30-minute hold, 5% of mission fuel contingency. All of these calculations having been done step by step from first principles Newtonian mechanics. I can run off-design missions. So the specific weight, let us reduce it to, let's say, 220 tons. And with a chosen payload mass, let's keep it unchanged for now. So in this case, we are down to 7,126 nautical miles and a block fuel burn of 71 tons. Again, fully iterated. And all the reserve requirements are fully iterated as necessary, for example, for the 5% mission fuel calculation. And here is an off-design mission at the required range, let us say 3,000 nautical miles. 3,000 nautical miles, block fuel burn 27.8 tons. And the required takeoff weight is about 174 tons. The fuel load 33.3 tons, calculated again in a fully iterated manner. I can do a payload range diagram. With 242 passengers, this would be our design range, 7725 down here. This part of the line is at MTOW. This is the fuel limited case, fuel capacity limited, and you can see that with zero payload ferry range, about 10,000 nautical miles, and this is the MZFW case up here. Takeoff and landing field length calculations. So FAR 25 takeoff field length about 9,000 feet. Second segment climb graded about 2.7%. Many other details. Landing field length at maximum landing weight 5,600 feet. and an approach speed VAP 141 knots, and a variety of other information. Again, field performance is calculated step by step, and we can do a plot of takeoff field length as a function of takeoff mass and airport altitude. Each color is a different pressure altitude. The dotted portions are areas where the takeoff flap is having to be gradually reduced to be able to meet the second segment climb graded requirements. And this kink here is typical of VMC, minimum control requirements. And this is done with flaps 15, except for these portions, and at ISA conditions. Note that there are inherent limitations in field performance calculations. This is a very dynamic phase of the flight. There are significant uncertainties in aerodynamics and ground effect. There is subjectivity in piloting assumptions, so the accuracy levels can't equal those of in-flight performance calculations. In-flight performance is highly accurate. Field calculations are still sufficient for all design assessment purposes, but they are not certification numbers. Another thing we can do is direct operating cost, DOC calculations. There are various traditional methods that can be used, all of which are effectively programmable. The default numbers are not up to date, but there are controlling parameters that are available, and you can set up your own definitions in effect. For example, I can load a different set of assumptions and do the calculations again. So this is a cash DOC only. I won't be using DOC in any serious way during these presentations. There are large uncertainties. Effectively, DOC is whatever you define it to be, and differences of 300 or 400% are not unusual in DOC calculations. But if you wish to use these, you can, and you can set them up as you wish. Getting back to performance calculations, as I said, this is our design range, and this is subject to certain assumptions of how the aircraft will be flown. So we can look at the range modes dialog, and this lets us define the flight levels that I will be using, the cruise Mach choices, and climb and descent speed schedule calculations, which are at the moment handled automatically by Piano, but you can enter your own speed schedules as well. So at the moment we're using this selection of flight levels. If I look at RVSM westbound, that's reduced vertical separation minima, that is the entire set. Eastbound RVSM, IFR semicircular rules, and you can choose or enter whatever values you want manually. We are flying at Mach 0.85, so if I click OK with these new flight levels and do my range calculation again, we are down to 7,693 nautical miles, slightly less but not much. I can also specify different reserve assumptions. So at the moment I'm using 5% contingency. If I enter a set of reserve rules with a 3% contingency and run the range again, we are now up to 7,883 nautical miles. Or if I enter US flag operations rules, these are quite old-fashioned and conservative with 10% flight time requirement. So the range has now gone down quite a long way to 7,438 nautical miles. And like before, I can go back to my original database definition, and I am back to my nominal design range. Another thing you can do is side-by-side comparisons for two or more aeroplanes. You can choose the things that you want to look at, and we will look at an Airbus definition of wing area and available thrust definitions. Let me select two different aeroplanes. There is an Aerospatiale 100, an old project. Let's pick up an A300 as well. And we run them both. You get a tabulation of the basic characteristics in a comparative sense. 3 views the schematics of the airplanes on top of each other. And payload range diagrams overlaid on the same picture. I will pause here and continue in the next clip.